Hello everyone, welcome to our webinar today. Coming with today is our speaker from Brazil, Behling. Rochers is an expert in the field of optimization and projection method in particular. So he's a professor of applied mathematics at Fundação Getúlio Vargas at Rio de Janeiro, Brazil. So he got his PhD in mathematics at IMPA in Rio de Janeiro and did a postdoc at Stanford University and the Technical University of Dresden. He also holds positions at Federal University of Santa Catarina in Brazil, where he's got his bachelor and master in mathematics. It's a very fortunate coincidence that we know each other. So I hope that we will see each other in person elsewhere. So at the meantime, welcome to Australia virtually. And thank you very much for your time with us. So now please take your stage.
Thank you. Now, I would like to start greeting everyone in the audience. And I would like to thank you, Hoa, all the organizers of this seminar, Dao, Kruger, Lee, and Rochina, and Matthew Tam. So it is a great honor for me to be giving a talk for the Australian community on continuous optimization. So I'm really flattered with the invitation. And as you said, so my name is Roger Behling. I work at Fundação Getúlio Vargas in Rio de Janeiro. I have a picture here. This is actually one of the views of our buildings. It is nice. And as you can see, the title of my talk is Circumcentering Projection Type Methods. And this is a joint work with Junior Belo Cruz from the Northern Illinois University, close to Chicago, and Professor Luis Rafael dos Santos from the Federal University of Santa Catarina in Blumenau, Brazil. And I usually say that the story of the circumcentered reflection method, which is the subject of this talk, goes back to 2016, when Junior, Luis Rafael, and me started with our meetings. But actually, I got somehow inspired by a work that I have together with Professor Yinyu Ye, Professor Fredo Yusen, who is in the audience from IMPA, and Andreas Fischer from the Technical University of Dresden in Germany. We worked on what is called the projected Liebenberg-Margot method, and choosing a suitable Liebenberg-Margot parameter, we derived convergence results for this method. And I saw some similarity of the projected Liebenberg-Margot method with the method of alternating projections. And I sort of had an idea of accelerating the projected Liebenberg-Margot method. And this somehow led us to introduce the circumcentered reflection method in 2016. Well, the content of my talk is based on 4 papers that we have published on the subject. The first one was published in 2018. It's called Circumcentering the Douglas-Rachfort Method. Here, our problem was the one of projecting a given point onto the intersection of 2 affine subspaces. Right? This is called the best approximation problem. It is a very simple problem. And we attacked this problem and introduced the circumcentered reflection method and proved that it works faster than the classical Douglas-Rachfort method. We then moved to the second paper published in Operations Research Letters. It is a short paper, but I like it very much, where we also had this best approximation problem involving affine subspaces, but now you have a finite number of them and possibly more than 2 affine subspaces. And the approach that we had in the second paper was quite different from what we derived from what we had in the first paper. And we were able to show that the circumcentered reflection method would solve past approximation problems involving a finite number of affine subspaces. In the third paper I'm going to talk about, our third paper, we also addressed the problem of projecting a given point onto the intersection of a finite number of affine subspaces, but now we had a composition of circumcenters. So this composition we called the blockwise circumcentered reflection method. We could solve now the same problem that we addressed in the second paper, but in with the composition of circumcenters. Yeah. This was not that easy. It was not trivial. We had to come up with a thing that we called best approximation mappings. And I guess there is a person here in the audience, Yu Young from the University of British Columbia. And she wrote an entire paper on best approximation mappings. And so all the analysis was based on this best approximation mappings that we call BAMs, right? And in this paper, we could also recover the famous method of alternating projections as a particular case of the blockwise CRM. And this was nice. And finally, in this fourth paper, we were able, under Pierrat's product space reformulation, to solve the general convex intersection problems. A problem that is, we were able to track a point belonging to the intersection of a finite number of closed convex sets. Right? So this is a summary of my talk. And at the end, I will briefly describe what we have done in a paper that was accepted last week. We had some other people joining us, Professor Frederik Jussen and his PhD student Reza, who is in the audience. And we're also working with approximate, instead of using actual reflections, we are able to use approximate reflections. And this we'll see briefly at the end of the talk. Let me talk about some technicalities. Many people in the audience here might know what the Douglas-Rachfort method is. For those who don't, let me explain this briefly. Here we have two affine sets, capital U and capital V. And our aim is to project a given point X onto the intersection of U and V. And the rules that you have, you can use projections or reflections with respect to U and V, right? And what does the Douglas-Rachfort method in this setting in order to track, in order to find, in this case, in my drawing, I have two lines. There is just one point in their intersection, in the intersection of U and V, which is X bar, as you can see, right? As you can see the hand here. So this X bar, if you are at a current iterate, say X, the Douglas-Rachfort method brings you to a point called Tx. In order to get this point, you reflect X through U, getting a point Y, and then you reflect Y with respect to capital V, getting Z. So you have X, Y, and Z, and the Douglas-Rachfort method takes the mean, the midpoint between X and Y. So this is Tx, as simple as that. Of course, this method solves problems more important than this one, and it is actually related to ADMM. Everybody likes this trendy ADMM, the alternating direction method of multipliers. So via duality, you have this connection. So it is a very important method. Here on my slide, you can see I have this remark. This Tx can be regarded as a Cimmino iteration as well, but computed at the point y. If I'm at the point y, I can compute reflections in parallel. Let's say one person reflects y through u, and another person reflects y through v, and then you have x and z. You take the barycenter of x and z, which in this case is just the midpoint between x and z, and this coincides here with Douglas-Rachfort point. So the Douglas-Rachfort method employs the composition of reflections, and the Cimmino method, at least the reflected method, uses it computes reflections in parallel. People familiar with the Douglas-Rachfort method know that the sequence generated by such an iteration does not always converge. But in this setting, we know that the shadow sequences, I mean, if you have the sequence generated by the Douglas-Rachfort method, and if you monitor the projections of this sequence onto U or onto V, these are the shadows. These shadows converge to your solution. But if you are in R2, you would have the convergence of the pure Douglas-Rachfort method here. This is important to know. One of the problems of the Douglas-Rachfort method is that even if you have this simple problem of finding a point in the intersection of two lines in R2, you might converge very slowly. So in this picture, you have this procedure. You start with x0, and the Douglas-Rachfort sequence is here in blue, and you converge very slowly to this point here in red. You have this spiraling behavior. And what we did was to avoid this to a certain extent with the circumcentered-reflection method. Another method that people like, very famous, it goes back to von Neumann in the 30s, Cox Marx, and so on, is the method of alternating projections. If you have an initial point here, x0, that you want to project onto the intersection of capital U and capital V, what you can do is you project x0 onto U, you project this point onto V, onto U, onto V, and so on. And this generates a sequence converging to a solution. It actually converges not only to a point in the intersection of U and V, it converges to the closest point in the intersection to this point, to this initial point, x0. Here, the problem with the method of alternating projections is that the angle of your affine subspaces is too small. This gives you a very bad zigzagging behavior. And this is something that we would like to avoid. And also in this regard, we wanted to provide a faster tool for solving these problems. This angle between U and V, by the way, is called the Friedrichs angle. So what have we done in our first paper? It is quite simple to understand. You have U, you have V, and you have this iterate X. You do something similar to what you have done in the Douglas-Rachfort method. You take X, you reflect this X with respect to U, get in Y. You reflect Y with respect to V, get in Z. And then you have this triangle with vertices X, Y, and Z immersed in Rn. And then you look for a point that lies on the affine subspace defined by X, Y, and Z. And that is equidistant to X, Y, and Z. This is the Euclidean circumcenter, the circumcenter that we learn in high school. You may ask if this circumcenter is well defined, and the answer is yes. And this is essentially due to the fact that reflections with respect to affine subspaces are isometries. And there is a nice work by Professor Bauschke, Yu Young, And I guess another researcher from the University of British Columbia in Canada. They are very interested in the circumcenters, and I'm flattered about this. And they prove that CRM, instead of using reflections, if you use general isometries, you also have convergence of the method, which is very nice. So how do we iterate? We have X, Y, and Z. This triangle, even if it is not determined by 3 distinct points, you always have a circumcenter. This is denoted here by C of X. And in my drawing, the problem is solved in one single step. This would always be the case here in R2, except if you start maybe with X on U, precisely on U, but then it will take you 2 iterations, but you have this finite termination of the method. And does this work? The answer is yes. And how did we do the analysis for this method? Our convergence analysis relied completely, almost completely, on the convergence analysis that was well established for the Douglas-Rachfort method, right? And how could we do that? We could inherit everything that had been done for the Douglas-Rachfort method. But how could we inherit these results? If you look at this picture, here I'm not drawing U and V. I only have this triangle, X, Y, and Z. I have the Douglas-Rachfort point, T of X, which is the midpoint here of X and Z. And then I have the circumcenter of this triangle, right? We were able to prove, and this was not that difficult, that the circumcenter here on the affine subspace defined by X, Y, and Z is the best point distance-wise to the solution, right? On this affine subspace of dimension of at most 2, right? And what happens is that the Douglas-Rachfort point lies on this affine subspace determined by X, Y, and Z. So we prove that we do better than any point here. In particular, we do better than the Douglas-Rachfort point. And this enabled us to get convergence. And more than that, we were able to prove that the circumcentered-reflection method, CRM, would converge linearly to a solution of the best approximation problem, and with a linear rate of at least given by the cosine of the Friedrichs angle. And this rate is known to be sharp for the Douglas-Rachfort method. This was proven by Junior, Bauschke, and some other authors. Yeah, and that's the story of the convergence analysis. I have already summarized everything. It is here on this slide. And we ran some experiments. And in this very simple setting, when you only have an affine subspace U and an affine subspace V, it is just impossible for the method of alternating projections and the Douglas-Rachfort method to beat us. It's just impossible. So we always do better in this setting. And even if you have small values of the Friedrichs angle, which you can see here on the right, and you have a performance profile showing that we do better than both DRM and MAP. But of course, this is just the beginning of the story. But, who is interested in a best approximation problem featuring 2 affine subspaces? Can we do something else? Can we do something more important? In our first paper, we have this toy examples here, these toy problems. They are non-affine. For example, here you have this closed ball and this tangent line. So the only point in the intersection of these 2 sets is X bar. And here what happens, you can see, in order to reach this solution up to a certain level of accuracy, starting from this point X0, at that time we called the method CDRM, the circumcentered Douglas-Rachfort method. Later on, we called it just CRM, circumcentered-reflection method. It takes us 17 iterations to reach this solution here. And the Douglas-Rachfort method takes 29 iterations and it does not converge to X bar. Here you can see what I call the shadow sequences. If you project this sequence in red onto the line or the ball, you converge to X bar. So for the shadow sequences to converge, it took 29 iterations for the Douglas-Rachfort method. This example here on the right, it shows you that we do much better than Douglas-Rachfort for finding this point in the intersection of these two balls. But interesting is that the first circumcenter step takes you farther from X bar than the Douglas-Rachfort method. But then you dive in and you converge. It is very fast. You reach X bar. Down here we have a simple example featuring a non-convex set. There is this young researcher, Lindstrom. He was in Australia, I guess. For a while, he worked with Jonathan Borwing. He's now in Hong Kong, and he has some work on circumcenters for non-convex problems. But what we can see here immediately, what we saw in our paper, is that if you have a non-affine problem, circumcenters might not even be well defined. If you start, for example, in this example here, on the line connecting the centers of these two balls, if you take your reflections getting the points y and z, so you have x, y, and z, they might be all on the same line and distinct. So we know that in this case, there is no circumcenter. We had issues with this method right away. Right? But we thought, okay, this is easy to overcome. When the circumcenter is not well defined, you could use either a Douglas-Rachfort point or something else, yeah, and then you keep going. But we thought that, for example, here, x0 is led up here. You get farther from your solution set. We thought that this could eventually happen, but then you eventually also would come back and reach the solution. And this is not true. So when we were sad for a while, this was shown by Aragon Artacho and some other co-authors, a group from Alicante, from Spain. They showed that the circumcentered reflection method for a non-affine example could diverge, right? This could be the end of the story for CRM, but it's not, you know? And I'm telling you, I will talk about some results today, but the best results are yet to come in the next few months. You're going to see something new in this regard. A question that arises too is whether we could solve best approximation problems featuring a finite number of affine subspaces. And the answer was yes. But now we had the problem that we could not rely on the convergence analysis of the Douglas-Rachfort method because my good friend Matthew Tam, who is in the audience, has this very nice drawing here together with Jonathan Borwing, where they show that if you try to generalize this DRM in a very pure form, it may fail to converge if you have more than two sets. In this case, we have three crossing lines. They cross at the origin. And if you start with a point here, x0, you reflect this through the blue line, and then through the red line, through the green line, you end up at the same point. So if you take the mean between x0 and this composition here of reflections, you stay there and you don't reach the origin, which is the only point in the intersection of these three lines. So we could not steal the convergence analysis anymore from the Douglas-Rachfort method. But we were able to define an auxiliary operator, that is firmly non-expansive. And what is nice is that this, the image of this operator lies exactly where we wanted it to lie, right? Because what do we want to do now? What is a circumcenter now when you have more than two sets? You have a point X, you reflect this point with respect to the first set, to the second, to the third, and then you get a cloud of m+1 points, and you want to try to find a point that equidists to all points in this cloud, and that lies in the affine subspace defined by the points of this cloud, right? And again, we could show that the circumcenter, again, it will be well defined because reflections through affine subspaces are isometries, and this essentially enables us to get the good definition of the circumcenter. And we could again prove that the circumcenter is the best possible point on the affine subspace defined by the cloud of m points that you got, distance-wise, regarding the distance to the solution set. Right? In particular, we do better than this operator here. We look at the fixed points of this operator A that we define here on this slide. And this is precisely your target set. Let me go back here. Where is it? Your target set is now this capital S. Right? And then the fixed points of A is precisely S. And we have shown that, you can see here, we do better than this linear operator with respect to the distance to the solution set, and we have this theorem. If you have any X in Rn, and you have M affine subspaces with non-empty intersection, the name of the intersection is capital X, and if this set capital X is non-empty, then you can create a sequence of circumcenter iterations that converge linearly to your solution of the best approximation problem. That is, the projection of X onto capital S. Right? And what is a circumcenter? Again, here to explain, what does it mean here? C of X is what? You have a point X, you reflect it through U1, you take this point, reflect this with respect to U2, and so on. And here I have this m+1 points that gives us our cloud of points. And then in the affine subspace defined by this cloud, you look for a point that is equidistant to all points in this cloud of reflections. And this circumcenter is always well defined because reflections through affine subspaces are isometries. Can you compute such a circumcenter? Yes. You have to solve a linear system of size m, and that arises from the intersection of bisectors. As in Euclidean geometry, you can write a linear system with this in mind, that you want bisectors to intersect. Then you have a linear system, you solve this, it has size m, and you have a circumcenter. And this is easier than solving the best approximation problem, right? Because you have an optimization problem. You're not only looking for a point in the intersection of U1, U2, U3 until UM. You want to take a point X and project it onto their intersection that here we call capital S. We were successful with this. And then in the third paper, we were able to do this in blocks. In order to illustrate this, I took here 7 affine subspaces, U1, U2, until U7, and I divide these affine subspaces in blocks. I have 3 blocks. In the first block, I have the affine subspace U1 and U2. In the second, I have U3, U4, U5, and U6. And in the third, I have U7. And then you create 3 circumcenter operators. And you have then the composition that we call the blockwise CRM. And what do we do? If you have a point xk, you reflect it through U1, through U2, and take a circumcenter, right? Take this circumcenter, reflect with respect to U3, U4, U5, U6. You have this composition of reflections, right? And then you compute a new circumcenter. And again, now in the last block, I only have one affine subspace. You take the last circumcenter, you reflect with respect to it, and take the circumcenter. If you only have one set in the block, your circumcenter regarding it will be just the midpoint of the last circumcenter and its reflection, right? And this gives you a projection. So the last circumcenter here on purpose is a projection. Right? This method works. As I said, we had to come up with some different techniques to show that this works. We defined what was called a best approximation mapping. And this enabled us to get this theorem saying that whenever you start in Rn, for any choice of blocks, you iterate in the way I explained, you get linear convergence to your best approximation solution regarding your initial point X. Okay. More than that, if you only have one block, so you put all these 7 affine subspaces in one single block, and all your affine subspaces happen to be hyperplanes, the circumcentered reflection method, or the blockwise, solves the problem in one single iteration. Now, if all your blocks only have one affine subspace, you only have one affine subspace in each block, the blockwise CRM becomes the famous method of alternating projections. Let me see here the chat. There's some people talking here. Okay, let me see what time it is.
I used to have like 20 minutes.
I still have, let me see, what time is it?
It's 9:30, 35.
Okay, 9:35. So I still have 15 minutes, yeah? Is that correct? 15 minutes or?
Yes,
9,
yes,
5,
or 10, like it's up to you.
We did some experiments with this blockwise CRM. My friend Luis Rafael, he got excited about running some experiments with this synthetic image, well-known image, the Shep-Logan phantom. This is here the original, in the picture A, you have the original picture, the original image. And then we recovered this image. We had data that was put into a linear system of equations. And then you can use the method of alternating projections to solve this linear system. And this provides an image. And this is, as I said, the blockwise CRM. All blocks have one single affine subspace. And then we looked at what happened if we have more
Speaker seems frozen to me.
I think,
for me also.
yeah, I think he has some connection issue.
Can someone else substitute the speaker? The
And
slide is on the screen.
We had 2 others co-author.
Okay.
I can talk about this picture if you want. Union also is here. Hello, people. My name is Luis Rafael Santos. I'm the co-author. I'm Salutio from Brazil. I was once in Australia. It was very nice, and I hope I come back. I can come back soon. Well, that picture, what Roger was talking about was that we could recover the Shep-Logan image. This is very, very well known in the community that works with computer tomography. And the fact is, as you could see, we had there only 10 iterations for the method, and it's very common including in the machines that are in the hospitals, that they use the method of alternating projection, because as you can see, even if you don't have a very high precision, you got a nice image for the doctor, for the medical doctor to see what he wants. So that's why these methods that use projections are reliable there. And in this case, we could see that only with 10 iterations, that was the
Rafael Roger is back.
Oh, great. Roger, I was just talking about your image, but you can put it again, and then you can go on. I was just explaining what the picture was. So I have to present myself.
It is actually your picture. Thank you for the support.
No, okay, go ahead, please.
Yeah. So you explained everything about this picture. I'm glad I'm back here.
I was just saying that. Yes, just to finalize my part here, what I was saying is that you don't need a very high precision to solve the linear system that becomes this image, and that's why a projection method is very reliable, and we could take a better picture using block CRMs than the pure method of alternating projection. That's what I was talking to them. So please continue now with your talk.
Thank you. Thank you, Luis Rafael. Yeah. So finally, we have a more important problem. We want to track a point belonging to the intersection of a finite number of closed convex sets. These sets are labeled here as xi. I goes from 1 to m. And their intersection, we assume it to be non-empty. It's denoted here by capital X. As I said in the beginning, Aragon Artacho and his co-authors from Alicante in Spain, they proved that CRM might diverge for a general convex intersection problem. So what is our hope in this regard? Is there
Roger,
hope?
allow me a part here. Matthew Tam was also in this paper, so he's here. It's due to hear also the picture, I guess.
Thank you, Tam, for Matthew for showing that we were diverging. But yeah, so this inspired us to come up with something that could solve this issue, could overcome this issue. And what we looked at was Pierre's product space reformulation. I call this capital W here the Cartesian set. It is given by the Cartesian product of x1, x2 until xm. So you have a set now in Rn times m. And this here is called the diagonal space. It is actually a subspace. You take a point in Rn times m belongs to this diagonal space. If you take a point in Rn and you replicate it m times, so this is the diagonal space. And it is very easy, it is straightforward to prove that there is a connection between these two problems. But now we only have two sets. But the price you have to pay is that the two sets that you've got are now in Rn times m and no longer in Rn. What we could do, we have shown that for a affine subspace U and a closed convex set K, you can apply CRM as long as you start on your affine set U. So this covers the problem that we have down here, because W is closed and convex, and D is, in this case, more than just an affine subspace. It is actually a subspace because the origin belongs to D, right? And we enforced CRM for this problem, the problem of finding a point in the intersection of a closed convex set and an affine subspace. We could prove that the circumcenter is well defined as long as you take an initial point on your affine subspace, and more than that, you always converge to a solution. So this sequence ZK is in Rn times M. It converges to some point. Do we have, say, Z bar, and then Z bar is the replication of some X bar, the replication of some X bar, you take it M times, and this X bar is a solution, if you use in Guérin's problem space reformulation of your initial general convex intersection problem. So, but we carried out an analysis looking at a closed convex set and an affine subspace. This drawing here gives us an idea of what is happening. And we can see that, so this is your current iterate. You are on U, this point Z. You reflect this point with respect to capital K, your closed convex set. You get this reflected point here. You reflect this point through capital U. You have this triangle, and then you look for a circumcenter. This circumcenter exists, and it lies here. This circumcenter can be seen, roughly speaking, as a Newton step, some sort of Newton step calculated at Z map, where Z map is the iterate provided by the method of alternating projections computed at Z. Look at this here. So this is Z. You project onto K and then onto U. This is Z map. And here we have this tangent line to this smooth set here in this drawing K. And this is our circumcenter. So there is a Newtonian flavor to what we have done, and this is nice. We carried out some numerical experiments comparing, again, CRM with Douglas-Rachfort method and the method of alternating projections. And we do better than these classical tools now in the product space reformulation. Again. That's it, basically. We had last week a paper accepted in computational optimization applications. In this paper, there is a union with Rafael, me, Professor Fredo Yusim, and also his PhD student, Reza. We were able to prove some, as you can see, so the title of this paper is "The Circumcenter-Reflection Method Achieves Better Rates Than Alternating Projections." Basically, what we had here was we assumed that we had some error-bound condition. And then under the error-bound condition, it is known that the method of alternating projections converges linearly. And we have shown that we have a better rate of convergence. We even have an example for which CRM converges superlinearly, while the method of alternating projections, it never reaches superlinear convergence. Only linear convergence can be expected. And currently we are finishing a paper on CRM, but instead of taking exact reflections, we take outer approximate reflections. And here we have a bunch of authors. Guilherme Araújo, he was my master's student. He defended his thesis 2 weeks ago. Professor Heinz Pauschke, who is well known in this field, he was in the committee. He praised the thesis. I was so happy about that. Reza is again in the paper. Me, Junior, Professor Yusen, and Luis Rafael. So this will be submitted soon. And this is what we are doing now, but we are pretty eager to address other problems. We have some dreams here. We want to apply CRM to everything, in particular to basis pursuit, to sparse affine, We want to investigate the possibility of achieving superlinear convergence. And I have some other stuff that I'm not allowed to talk about. My co-authors, they don't want me to talk about this. That's why I put here content hidden. And I'm always happy to share the ideas, but I'm not allowed to today. In this slide, I put in blue people who worked on circumcenters. You have the researchers from the University of British Columbia, people from Hong Kong, people from Spain, and I'm very happy that this grabbed the attention of some well-known researchers and that people got excited about this circumcenters. They got interested in this. And last week we had this on arXiv just appeared. Let me see. I cannot see here the last paper. A paper on circumcenters regarding Bregman distances by Hu Yang, who is in the audience. So it's very nice to see people working on this. And finally, I have to admit, I cannot deny that I would like to be in person in Australia. Eventually this is going to happen, but by now I put this beautiful picture of Sydney. I understand that Luis Rafael, my co-author, he was in Australia already and he loved it. I don't know if Junior was there. I'm pretty sure that Alfredo Yusim was there because maybe because of Regina, right? Regina
Yeah,
Bereshit,
exactly.
who is a professor.
I visited Regina in Adelaide a few years ago. Yeah, some 10
nice,
years.
Yeah. Because Regina Bereshit, that is well known in Australia, she is my academic sister. I don't think she's in the audience. There were some people who talked to me who couldn't attend the talk. Yeah, that's it. Basically, thank you very much for your attention. I guess you have an idea of what we have done in the last 5 years. I want to thank Junior and Luis Rafael. We have been in sync for over 5 years. So nice to work with you. Thank you.
Thank you, Roger, for your very nice talk. So we have time for questions to our speaker. So anyone just unmute yourself and then ask a question or just write on the chat.
May I ask a short question?
You may, yeah.
Who's asking?
Thank you, Hua, and thank you, Roger, for this nice presentation. Now we know a bit more about those centers. And a good thing is that actually it went well, even when you disappeared for a few minutes. It's good to have a team in general, and particularly when members of the team can easily substitute each other. My question is about elementary things. In the very beginning of your presentation, you illustrated alternating projections on two settings with different Friedrich angles. And of course, this angle or error bounds, which you mentioned closer to the end of your talk, this regularity or transversality assumptions of course, are important for the convergence analysis. What about your improved method? Do you see similar effects depending on the regularity constant or Friedrich's angle or something like that? And a continuation of this question, in some of your examples, you even had this Friedrich's angle equal 0. And you also mentioned, and we know that in such a situation, we cannot guarantee, for instance, linear convergence. And you also mentioned a negative example by Aragon Artacho and his friends from Alicante. And then you told us that you found a way to make your method still work, even under those bad circumstances. And when you say that it works, can you also make an estimate of convergence rates in such bad situations?
Definitely. Thank you very much for your question. even if your Friedrichs angle, when you have a general convex set, is 0, so you have no error bound, so to say, right? You can achieve, for example, linear convergence. If you look at a quadratic function, say y equal to x squared, you look at the epigraph of this function and you look at the x-axis, so you have no error bound. But if you apply CRM to this particular problem, you get linear convergence, right? And so for MAP, this is impossible for the method of alternating projections. So we are able to speed up, we are able to move from sublinear to linear in this particular case, and this happens with other examples, right? So, but on the other hand, if you take something that Professor Houston calls a Cauchy ball, if you look at the function e to the power of -1 divided by x squared, so even the CRM converges sublinearly, right? In this case, you have no error bound at all. I mean, the derivatives don't have error bounds, and so we can be slow as well. But other than that, we very often get better convergence. In particular, we have in one of our papers, we have an example in which MAP only converges linearly and CRM converges superlinearly. So there is a jump in the speed of convergence.
Does it mean that you still use some other regularity assumption different from Friedrichs angle, or you don't use anything at all?
In the paper where we looked at error bounds, we had the standard error bound, which says that the Friedrichs angle is non-zero. Then we had particular instances in which so we had epigraphs and the derivatives involved. They provided some error bounds, but for example, if you have the epigraph of x to the power of 4, and you look at the intersection of this epigraph with the x-axis, then I guess in this case you still have linear convergence of CRM, while MAP converges only sublinearly. Well, I don't know if I answered your question.
If you allow me, Roger, yes, there is some regularity. In this case, the regularity would be of higher order. I mean,
exactly.
But there are some regularity. In cases where you have no regularity at all, like he was saying, this Cauchy basin, which has it's infinitely differentiable, but the derivatives are 0 for all orders, then the CRM is sublinear, and there is nothing to be done, but still converges, but sublinearly.
Okay, thank you. And with these two examples, which are now on the screen, can you say, can you compare the convergence of your method on these two examples?
Yes.
Yeah, in this case, we are in R2, and then the CRM method converges in one single step, because these two lines,
in both cases.
Exactly, because they happen to be hyperplanes in R2. So these are hyperplanes in R2, and we proved that the full block CRM, which we have here in R2, converges in a finite number of steps, usually essentially in one single step. So this was also our motivation. You have the simple problem in R2, you want to solve this in one single step, and CRM does this. But this is not the case in general, right?
Yeah.
But if you allow me, when you have an error bound, let's say classical error bound, which would be like the cosine of that angle, CRM gets, I mean, in the case of alternate projections, well, the asymptotic error bound, asymptotic constant of the linear convergence would be just that cosine. In the case of CRM, it's something which is better. It's extremely better, and we have a formula, a specific formula, which will give something better than the cosine. This is the paper which was recently published, not well, accepted in computational optimization applications. We get a real improvement in convergence rate.
I'm intrigued. Thank you.
Thank you. Thank you for your question.
Thanks.
There is
Sorry for interrupting it.
No, of course not. Of course not. We are a team, so we are.
Oh, we have a question from Gary in the chat.
Yeah, there's a question here on the chat. You want to read it or want me to read it?
I will read it. Have you explored any connection between block CRM interaction and the use of a preconditioner to solve a linear system? In particular, using a careful choice of blocks to optimize the preconditioner. I think Gary, you can unmute yourself and then ask the question because you were here.
Thanks. Look, as I understand it, full block CRM would be effectively solution of the linear system. So if you're using sub blocks, I would guess it's sort of like you're constructing an approximation to the full matrix in the original system. And then iterating the sub block CRM would be sort of like multiplied by a preconditioner and then iteratively solving the preconditioned system. And there's a lot of interest, of course, in choice of really good, efficient preconditioners for very large linear systems. And I was just wondering if your thoughts had strayed in that direction.
Thank you very much, Gary, for your question. In our paper, we had a linear system arising from PDE, and it had a certain structure. I mean, you could see the structure in our paper. You can see. So there were already blocks there, and we explored this structure. And so this kind of maybe answers a little bit of your question. And so we looked at the structure of the matrix that had blocks already, and we used blocks regarding this structure, and it kind of worked fine. But maybe Luis Rafael can say something about this, because he's the guy who does the coding and does the coding in Julian.
Thank you, Gary, for your question. This is a very, very nice question. Great idea, because what we did there, we wanted to solve the linear system. So we saw this structure is very, very well known. All these applied mathematics problems have, of course, this structure, and we never thought about the preconditioning thing. So I guess this is a very nice idea, because
Definitely.
The main thing is we cannot solve if we have few blocks, you cannot solve in a small number of iterations, but you are approximating because of the theorem that we proved. So you are getting closer and closer to the solution to the best approximation solution, better yet, and you can use it probably as a preconditioner for another good solver, like for instance CG or something like that away from the solution you need a good preconditioner. So I guess this is a very nice idea to explore in the numerical linear algebra aspect of CRM. Thank you for that. And
I just add
very nice view.
One thought to it was just that I'm glad it was something new for you to consider. But one thought in particular was that I've seen a lot on, there's been a lot of thought on how to construct good preconditioners. I was just wondering whether CRM would bring a new way of looking at how you constructed the preconditioner, if you see what I mean. And in particular, some of those properties about being a locally optimal approximator, or at least on affine subspaces, and whether that then sort of translated into even better preconditioners. So
this would be awesome, right? This would be
right.
Would be very nice. This one. were the case. Yeah.
That's the avenue that we never thought to cross, but it's very nice, very nice.
And anyway, I'll leave you to think about it a little bit, right? But
Thank you for that.
I have another. Sorry, I have another practical question. When you solve for this center point, you have to basically, I mean, if you have n hyperplanes, for example, you have to satisfy n conditions, right? But I mean, the original problem is a problem with n conditions. So isn't solving for the center point as hard as solving the original problem?
Yeah, in this case, you are not only tracking a point in the intersection of affine subspaces, you are solving the best approximation solution because you are projecting your initial point onto this intersection. So it is slightly different. Yeah.
So you're getting an additional benefit. But if you just wanted to solve, if you just wanted to find a solution or the solution of a system AX equals B, then you would in every step put as much effort in computing the center roughly as for solving the entire system.
If you consider the full block CRM, yes.
Yeah.
So,
okay,
so
then
this would be, I understand that this would be, maybe we are just looking at the problem in a different way or rewriting the problem, right? But of course, we have the benefit of solving this projection problem, right?
Yeah, I mean, and you can go beyond this, so you don't have to look at only linear subspaces, and so you can treat problems that are more complicated. You still get error estimates. So, I mean, you have a point, yeah? I'm just wondering, like, for the things I'm doing, whether this gives me something new or probably not. And we are also thinking about line searches. And then if you want to do a line search in order to improve a certain method, then maybe your method, because it's locally optimal, gives a very nice upper bound and a very good benchmark for comparison.
Well, I think this might be the case, yeah. That this method may provide, step lengths, right?
Yeah. So that is a very nice addition, I think, to what we currently have. So thanks.
Oh, thank you.
One thing I can add is that, as you can see, of course, you are solving n by m linear system, the same thing. The two things that happen is that you can solve it using Cholesky factorization to find. So this might be something that it's nice. And the other thing is that because of the block structure, you can made a little bit of payoff. You can say, like, oh, I won't solve a large system, but I solve small systems, and I will get closer to the solution. That's the payoff you can have if you don't want to solve the full linear system. Just to add, but you're right. You can use locally to maybe improve the solution or something like that.
Yeah, thank you very much.
Thank you.
Thank you. Is there any other questions for our speaker? I think we can. Thank you very much, Roger, for your very nice talk, and everyone for attending the seminar. I think we can close the seminar.
Goodbye,
Thank
everybody.
you so much. It was very nice to meet you. I hope I have the possibility to go to Australia in the near future. So I wish you all the best.
Yeah.
Excellent presentation, Roger. Excellent. Congratulations.
Thank you so much, Professor.
Thank you, Roger. Thank you, and all the best to Brazil.
Thank you.
Thank you, Juan, and Matthew, for the invitation. Bye-bye.
Stay safe.
Stay safe, guys. Bye-bye.
Yeah.
Thank you for a good talk.